Good afternoon. So, any question before we start? All right, the last method that we are covering for one-dimensional is cubic interpolation. So this method is gonna be under it's one of the methods at which we need to know the derivative information. So cubic and it's gonna do the refinement phase for one-dimensional search problems at which we have only one variable. So after we finish this, we are gonna start the method with n variables and no constraint. So what we are going to do, we are given with objective function of fx. We approximate that with q alpha, which is a quadratic function like this, a plus b alpha plus c alpha squared plus d alpha cubed. So we approximate the original function with the cubic function at 2 points. We pick 2 points, alpha A and alpha B. We plug in alpha A in fx, we find fa. We plug in alpha b in fb, we find fb. Also, we need to know the value of the derivative of objective function at this point. So we call it f prime a, f prime b. So what I did, I just plugged in point alpha a in fx. I calculated fa. I did it for point b, which is alpha b. I find fb, and also I differentiate this. I could find the value of derivative at point a. I named it f prime a. I did it for point b. I named it f prime b. So how many information do we have? 1, 2, 3, 4. At point alpha a, the value of the objective function is fa. At point b, the value of objective function is fb. At point a, the derivative is f prime a. At point b, the derivative is going to be f prime b. How many terms I need to find? A, B, C, D to approximate, to find the approximation of fx with this quadratic. So I can solve for A through D. Find fa, fb, f prime a, and f prime b, and solve for A, B, C, and D. So if I plug in alpha a here, I'm gonna get on the left side. I'm gonna get fa. Q at point alpha is fa equals to a plus b alpha a plus c alpha a squared plus d alpha a cubic, and fp would be a plus b alpha b plus b alpha b squared plus b alpha b cubic. Now, derivative of q is going to be q prime B plus 2C alpha plus 3B alpha squared. Now, if I plug in alpha A here, the Q prime of alpha is going to be F prime A. So F prime A would be B plus 2C alpha A plus 3CD alpha A squared. Same thing for alpha B. Alpha B has the derivative equals to F prime B. So the value of that is given. We already calculated that. On the right side, it should satisfy this. So I can write 2C alpha B plus 3C D alpha B squared. Now, if I want to find the optimum point at the cubic interpolation of fx, I should apply the necessary condition. In necessary condition, I should set q prime of alpha equals to 0 to find the candidacy for optimum point. If I set it equals to 0, I should find the roots of this quadratic function. Roots of this is negative 2c plus and minus a square root of 4c squared minus 4 times b times 3d minus 12 bd divided by 2 times this, which is 6d. Okay? Make sense? So how do I know that it's an optimum point? I should apply sufficient condition. What does it mean? The second derivative for b square of q, the alpha squared should be positive. Second derivative of this is going to be q at alpha star. It's going to be 2c plus 6d times alpha star. I'm plugging alpha star here. I will get 2c plus 6d times negative 2c plus and minus 4c squared minus 12bd divided by 6d. I can cancel out these two 6d. So I'm going to have 2c plus negative 2c. These two can be cancelled out. So the second derivative of the cubic interpolation is going to be positive 4c squared minus 12bd and negative square root of this if we pick this one. Since the second derivative must be positive, a square root is always positive. So the negative sign is not acceptable. So the alpha star that we pick as a optimum point would be 2c plus 4c squared minus 12bd divided by 6d. If I take 2 out of the square root, is going to be c plus c squared minus 3bd divided by d. So this is the optimum. And 3d. I forgot. 6 divided by 2 is going to be 3. I forgot 3. This is the optimum point for cubic interpolation function. So now I would like to pick 2 points. Assume point A and B are chosen such that the point A and B, meaning alpha A and alpha B. I pick alpha A 0 and alpha B greater than 0. Okay, I pick these 2 points. On this equation, and here, as I said, we have 1, 2, 3, 4. 4 equations to solve for A, B, C, and D. On very first equation, and this one, plug in alpha A equals to 0. B times 0 would be 0. This term is gone. This term is gone. So A would be equals to FA. Make sense? Equation 1. Equation 2. Alpha A is 0. This term is gone. B is going to be F prime A. First derivative of objective function at point 0, it's going to be the coefficient B. Now in these 2 equations, I'm going to have these 2 equations. FB equals to A, which is FA, plus B, which is F prime of A, alpha B, plus C, alpha alpha B squared, plus D, alpha B. This is one equation. Second equation, F prime of B would be B, which I already find the value of that F prime of A, plus 2C alpha A, alpha B side, plus 3D alpha B squared. So in these 2 equations, we are solving for C and D. I'm not showing the process, I'm just writing C and D right here. C is gonna be -1 alpha B times the bracket of 3 FA minus FB divided by alpha B plus 2 F prime A plus F prime A. One of the methods that you should do for homework 3 on problem 2 is asking you to apply the cubic interpolation. So I have not started the method yet. We are just driving these terms, then I'm going to talk about the algorithm. So coefficient C is going to look like this, D, like this, and coefficient D is going to be 1 over the square of alpha B, 2 FA minus FB divided by alpha B this is D. alpha star. So alpha star is whatever is the coefficient c plus a square root of c squared minus 3b times d divided by 3d. If I plug in the number, the equations over there, I will find alpha star like this. Alpha b times f in a. Before I do that, let me define an intermediate variable just to simplify the notation. I would like to simplify the notation. I define parameter z as a 3 times fa minus fb divided by alpha b plus f print a plus f print b. It's just intermediate variable. If you look at this, 3fa minus fb divided by alpha b, one of the f print a plus one of the f print b plus the f print b is going to give me z plus f print a. So it's going to be negative 1 over alpha b times z plus f print a. And this one is going to change to alpha square of b. Three here, 2z, uh, 2z plus f print a plus f print b. If I play with this, I will get that one. So if I plug in C, A, B, C, and D, and alpha star equation, I will get alpha b times parentheses f print a plus z plus a square root of z squared minus f print a. Close the parentheses. F print a plus f print b plus 2z. This is the optimum point of cubic interpolation of original objective function, where first point is 0, second point is positive. Here I assume first point is 0. So if I want to remove this condition and generalize this one for any alpha A and alpha B. If I do that, Z value is not going to change. Z still is going to be 3. We can prove. I'm not showing the steps, but Z is not going to change, but alpha star is changing slightly. Alpha B is going to change to alpha B minus alpha A. Times on the top of this I have f print A, which is plus z, the same, plus square root of z squared minus f prime a, f prime b. It's gonna be the same, and here it's gonna be the same. So the only thing which you need to change is alpha, b is gonna change to alpha b minus alpha a. Now I'm ready to talk about the algorithm. Step 1, apply bounding phase to locate two points A and B such that point A, that we call it alpha, is less than point B, and they have different sign on the first derivative. If you recall, if you remember, if this is the point, optimum point, if this is point alpha A and this is point alpha B, the slope of the line, which is tangent to the objective function at point alpha A and alpha B, is going to be f prime A and f prime B. The slope should have, the multiplication should be negative, meaning that the slope of this line is opposite to the slope of the other line. So this is going to guarantee that. Step 2. Compute alpha star using equation 1. I call this equation. Step 3. If the absolute value of first derivative of objective function at this point is a small number, meaning that this point is the optimum point, we should stop. Stop. We terminate the method, we introduce alpha star as a optimal point. If f prime of alpha star times f prime of A is negative, if this multiplication is negative, it means the optimum point is locating between alpha star and A. So if the multiplication of first derivative are negative, it means that the optimum point X star is between alpha star and alpha. True? So if this is the case, we set alpha b equals the new alpha b is going to be equal to alpha star. And f prime of b would be f prime of alpha star. And go to step 2. Go to step 2. Again, compute alpha star using equation 1. If this is less than determination criteria, we introduce that as the optimum point. Otherwise, you come again to this one. So if this is not true, else if f prime of alpha star times f prime b is negative. It means the x star is going to be between alpha star and the upper bound, which is the alpha b. Set alpha a equals to alpha star, f prime of a equals to f prime of alpha star. But again, we should go to the step. I'm going to work on one example to apply the cubic interpolation. Any question on this? All right, let's work on one example. Let me have this here. I'm working on example. So we would like to minimize fx equals to x power 5 minus 5 x power 3 plus 20 minus 20x squared plus 5 using cubic interpolation. Stop when the determination criteria is f prime at x star is less than or equals to 0.003. This termination. We assume that the bounding phase has the interval as 0 and 3.2. So lower bound for alpha A, the first point is 0, alpha B is 3.2. First, let me up. So this is the interval. It's telling me that alpha A is 0, alpha B is 3.2. F at point A. If I plug in 0 here, 0, 0, 0 plus 5. 5. What will be the F prime at this point? If you differentiate these with respect to time, with respect to x, you will get 5x4 minus 25x squared minus 40x. It should be negative 20x, not 20x. So remove the square. So f prime of x is going to be 5x4 power 4 negative 15x squared negative 20. At point 0, which is point alpha A, the f prime is going to be negative 20. Do the same thing for point B. Plug in 3.2 in the original function, 11.3. It's going to be 350.68. As you see, f prime A is negative, f prime B is positive. The multiplication is negative. We expected that because we know that point A and B are the lower bound and the upper bound of the optimum point. This multiplication should be negative, which is so next step is compute alpha star. To compute alpha star, I need to know z. Z value is 3 times FA 5 minus FB 11.3 divided by XB, which is 3.2, minus XA, which is 0, plus F prime A, negative 20, plus 350.68. Z is going to be 229.5. From question 1, alpha star would be 1.84. If I plug in alpha B 3.2, alpha is 0, F prime A negative 20, Z to 29.58, and do calculation inside the square root and divide by this one, I will end up to 104. And the value of objective function at this point negative 13. If I plug in 1.84 under objective function, I will end up to so now we should check if f prime alpha star times, sorry, this is the f prime of alpha star, it's negative. We should check if this is true or this one is true. F prime of alpha star negative 13 times f prime of A, which is negative 20. Both are negative, so the multiplication is very positive. So this one is going to be true. Negative 13 times this is going to be true. So f prime A times f prime B is negative. So then alpha A will be alpha star alpha b is gonna be 3.2. So the optimum point is gonna be greater than 1.84, less than 3.2. Then we go to step 2. And continue. Any question on this? So we are done with one-dimensional search method. What do I mean by one-dimensional? We only have one variable. We learned that we should apply the bounding phase first to locate the optimal point between lower bound and upper bound, then apply different methods to refine the interval to get a lower uncertainty on the interval. So now we are ready to move on n constraint problems. The homework 3 is gonna be 2 weeks from today. After you are done with the coding of homework 3, you are gonna use that code for homework 4. Homework 4 is gonna be, I can say, the most challenging homework for this course. When I go next week on Wednesday, I'm going to talk about the problem that you are supposed to work on that, but you need to study and learn some numerical methods to calculate algorithm. Not algorithm, logarithm. So I will talk about that shortly on next Wednesday. Simpson method is going to be applied there. I'm going to post a description about those, but you need to go out and find some resources to see how can you set up this method on your code. Also, you need to solve second order differential equation by using the MATLAB. I'm going to talk about that. How can we, this is second order. How can we change it to the two first order system of equation, and then we are going to talk shortly about the method that you can apply to solve this system of equation to find this. So then you are going to use the code that you have written on homework 3 to find the optimum value for the objective function that I have defined on homework 4. But as I said, homework 4 is the most challenging homework in this course. You have 2 weeks for that as well. title, we are gonna talk about the unconstrained problems in n variable. We would like to solve this problem. Find, you have n variables, so our optimum point is x star. It has the term of x1 up to xn. Which minimizes fx. So our objective function has n variable something like this. We would like to find numerical methods to find x star such that it can minimize the objective function. So in all methods, what we are going to do is given an estimate, we can call it a starting guess. I will call it an estimate. Xi at the optimum point. So you make a guess. You guess Xi is the optimum solution. Next step, find and improve estimate xi plus 1 such that, so you are moving from point xi to point xi plus 1 such that f at this point has a better value than previous point. So this is what we are going to do in the method that we introduced. We are starting always from the starting point. You make a guess on that, then you move to the next point such that it has a better or at least equal value of the previous point. And then from this point you move to the next point until the end of the optimum. This is the idea. So since we are working, we have a vector, we don't have one variable, we have n variable. The next point is moving from previous point in direction of SI. SI is a vector, and lambda I is a scalar. So first you need to determine in which direction you should move, then this guy is going to tell you how far you should move on that direction. So now let me talk about search techniques. Like the one-dimensional I'm going to talk about the different methods or technique that we are going to apply in this course. For n one dimensional is going to change to the n dimensional problem, search problem. I can have two categories. I mean, one direct search at which no need for derivative information. I don't need any derivative information. And second method, descent method. This method requires derivative information. Direct search consists of random search, or random walk. Univariate method. Pattern method. And pattern search or method, it doesn't matter what. We are going to go one by one, power method or search, it doesn't matter which. Descent method has been can be classified into subcategories. The method at which we need only gradient information or first derivative of objective function. Gradient, if you remember, when we have n variable, the first derivative is going to be a vector. Gradient of f would be del f del x1. Second, del f del x2 up to del f del xn. So the methods that I'm going to introduce shortly, they need we need to provide the derivative information or gradient information. These methods, we need to provide second derivative or a Hessian matrix. I'm just recalling, I mean, the test, I mean, this is the Hessian matrix, n by n. So the methods, the first method that we are going to cover in this is descent method. Second one is conjugate gradient. We are covering all this method, and this is going to be near term method and Qubic this is how we can categorize the different methods. Two main subcategories, which is direct search and descent method. Direct search are method at which we don't need any derivative information. Descent method, we need the derivative information. Under direct search method, we are going to talk about random walk or random search, univariate method, pattern search or pattern method, and powered method. One of the exam problem last 2 years ago was I gave one problem and asked the student to apply the power strategy. That's right. And this one we are covering this method. After we cover this chapter, we go to the linear programming, which is chapter 3 and 4. Before that, we have an exam, I believe. Then we cover chapter 3 and 4. Then we go to the constraint problem in n variable, the most general case, which is going to be the last type of the problem. Good? All right. Since the method is going to take longer, I'll stop here. On Monday, we are going to talk about, we are going to start from random walk. We go one by one. And going through this. Any questions? All right. So I'm collecting the homeworks, and you already have access to the homework. I'll post the solution for this one as well. I already posted solution for homework.